So in the previous lecture we talked about functions in terms of sort of theoretical considerations, and in this short lecture we will take the lessons from the previous lecture and try to sort of convert them into F sharp. We haven't talked so much about F sharp yet, but I think it will still be possible to follow along. So the first lesson we had in the previous lecture was 1. Functions are data. Functions are just the same as data. We saw that any function could be in principle written or represented as a table. It might be an infinite table, but it's just table data, mapping one value to another. And that was the first thing. And since it's data, for us programmers, it's kind of easy. We know that functions, typically as procedures of functions, they take data and produce data. So now, since functions are data, we realize that we could actually have functions which would take functions and produce functions. And it's quite natural since it's just data. There's like really no difference from what we have been doing before. But we could use this to our advantage. So the second thing we looked at was the fact that we saw that a function returning a function is just the same as a multivariate So that was sort of the essence of having a function return a function. That's the same as a function of 2 variables. And if you have a function returning a function, then it's a function of 3 variables. And then we saw that we could actually, instead of having a function returning a function returning a value, we could just, it was isomorphic or identical to a function of taking a pair and returning a value. So these two are just the different sides of the same coin, different representations, and we could swap between them. And we had 2 terms for that. We had the curry and uncurry. And the third thing we had was that we had actually functions which could take a function as an argument and then return a value. That value could of course be a function. So we could have a function taking a function returning a function. We can have a function taking a function returning a simple value, just some simple piece of data. And those we call higher order functions, HOF. And now we're going to look a little bit at these aspects of functions, but using F sharp syntax to see what this is. So let's start with the partial application. So in F sharp we can define a function by using the keyword let. Let is basically a keyword to bind a value to a name. So we can call this name f, and let is also the keyword for defining functions. So we could say let f of x equals x plus 1, and this is just the same as saying f of x equals x plus 1 in a language like C, where curly braces, of course, whatever. Have all the. So we see that in F sharp we have a slightly slightly tertiary syntax. There are no parentheses, and I'll come back to that in a little while. So this is defining a function in F sharp. We can define a value in F sharp by saying let v equals 42. Then we just say that, okay, the v is now 42 from this point on and forever, and it can never change. So in order to define a function of two variables, let's call it g, we can say g equals, g of x and y equals, well, x plus y, for example, to make a really simple addition function. And now we could call g in F sharp, we could call it by saying, well, g1, 2, and that would return a value which would be 3. Again, no parentheses here, and that's important. So, if we would look at the type signature, and we haven't talked about types and type signatures and such things yet, but we can look at how would this look in the sort of function syntax that we used previously. We're going to look at this. So this would be, this g here would be some, maybe a b, and a c. And this is exactly how we looked at how sort of we wrote in the previous lecture. And in fact, it turns out that this is pretty much a valid type signature in Haskell. So in Haskell and in F sharp, and we could just replace a here with, for example, an int and an int and an int. And this is just, g is a function which takes an integer and returns a function which takes an integer, which given an integer produces an integer. Argument 1, argument 2, result. And when we have the function in this form, we could use this fact that it's actually a function returning a function, which we can then call to produce a value. So now we could actually say let age equals, and now look, there are no arguments to x, nothing. This is just saying give the name x, the name age, the value 42, but instead of 42 I will say g5. And what I now do here is that I actually call this function g here with a single argument. Which means that what it returns is this thing. So if I would look at the type signature of age here, it would say age is a function from int to int, which is a function of one variable. And now I can just call age 5, and that would produce the final result 10. And we say that this 5 here is stored inside of age in a closure. So this is partial application at work. This is how it looks in real life F sharp code. I can define this g like this. This is a valid F sharp definition of a function. I can call g and bind the result of that like any variable. I don't care whether it's a number or a function, but since it's a function, I can apply it again to some new value to produce the final value of it. So that's pretty cool. In the next lecture, we will talk about lambda functions, but I will introduce the syntax of a lambda function just to show you how we can do this exact same thing, but with a slightly different syntax, which is equally valid and in principle equivalent. And I say in principle because there are some technicalities there behind the scenes which make them then not quite, but for all practical purposes, in this case, it doesn't matter. So instead of defining let g x y to be like this, I could say let g of x equals fun y arrow x plus y. So now I've defined g to be a function of one variable, which returns explicitly a lambda function. The fun says create a function on the fly, takes a single variable y and return this. So this is the exact same thing as this. Caveat, not exact, but almost. Like for this, it doesn't really matter. And of course I could do a g in a different way. I could say let g equals fun x arrow fun y arrow x plus y, and this would be the same as that. They're all the same. And of course I could rationalize this whole thing and I could say, well, fun x y equals x plus y. But I could still partially apply it. So these are just 3-4 different ways of saying the same thing, where this is explicitly saying g is a thing which returns a function, which returns a function, which returns the value. And now you can see, well, okay, this is just a function, so I can just, and I call it, and I get this function back, and then, and it sort of makes your head explode before you get used to it. But once you get used to it, you don't even think about it. This becomes second nature as you become functional programmers. So that was about partial application. So the other case we looked at. Oh, yeah, before we continue. So, okay, how could the other way of defining g? Well, I'm going to call this g prime. The prime is just a normal character in this case. It doesn't mean anything special. This is just, instead of saying g1, g2, g3, I can put this tick on it. And it just means that this is g, but it's slightly different than the original. I could say let g, and then I could say, well, g takes a tuple argument, x and y, and look at the, now I have parentheses. And that's x plus y. And there's a very subtle but important thing here. This definition here states that g prime takes a single argument. If I would write down g prime, it would be a to b, where a now is a pair. So in this case we probably have int, the pair of two ints. And the reason I can write this is something we'll talk much more about later. This is called pattern matching. It will take a pair and it will unpack it so that we can use what the pair contains. And we can do the same with triples and quadruples and so on. Another way of doing this, let's call it g prime prime, which is again the same function but slightly different, is to say g, and I'm going to say p, which is now a pair, equals, and then I can say, okay, I'm going to have to use a function to pull out the first element of that pair. That there's a function called fst. I can apply it to p, and I can say snd, and apply it to p, and that pulls out the second element of a pair. Again, same story. So all these g's that I have written down are, in at least in theory, completely equivalent. They're all the same, just different ways of expressing the same thing. Now the problem that, or it's not really a problem, but the sort of downside to having this form is that this cannot be partially applied because there is only one argument. I cannot give just half a pair. There is no such thing. Either it's a pair or it's not. And if I give a pair, I have to give a pair. So there's no way I can partially apply this thing. So that's an inconvenience of it. But this form is very useful when communicating in F# with the rest of the world, namely the stuff that is in the .NET framework, written in Visual Basic or in C# or C++ on .NET, because they expect everything to be tupled. So then in those cases where you want to communicate over these language barriers, this is the way to go. Yes. All right. So let's have a look. So the other case that we had, that was the higher order function. So let's define a new, let's call it age. This is a new age that we're gonna have. So age would be a function. I would say that it's going to take two arguments. I could have it take one, but let's, for the sake of it, have it take two arguments. I'm going to call the first one f and the other one x. I haven't said anything what these arguments are yet, but what I could say is inside here that this would be f applied on x plus x, for example, or something else. But now we can see that if we look at this definition here, I say f applied on x, that implies that this must be a function, and it must be, f must have a signature of some type A to some type B. In this case, probably we can say that int to int, so that I can apply it. If f would be just an integer or a float or something else, I couldn't apply it to an x, and then this would absolutely fail. So since I'm doing this f called with x as an argument, it has to be a function. And then that produces a value, which is an int, and then I can add it to x, which is an int, to produce a final value. Yes? So that's nice. So let's try and create some f. So we can create a function which I will call q, which might be, for example, q of x equals x minus 1. Simple function. And now I can call age with q and 5. So now we can replace f here with q, which would be 5 minus 1 plus 5, and this whole thing would return 9. Ta-da! So I can call a function, define a function and put it in there. And of course, what I can do now is I can do create a new function, let q prime, which of x, which would be x squared minus 1. And then I can just call age with q prime 5, and that would be 25 minus 1, which would be 24 plus 5, would give me 29. And this is the cool thing with the higher order function is that, and I will later show loads of examples of how this is useful, but this allows us to factor out some common behavior into this function age, or this higher order function, which is only dependent on sort of the structure of the problem. And then I can let the peculiarities of the problem go into this other function. So this is a fantastic way of abstracting away loads of details and you avoid repetition. So that's one of the reasons why these higher order functions are so useful and all over the place in functional programming, because they let us take out the structure of a problem, and then we can just specialize the problem by adding all the peculiarities of that particular thing into this queue. Is it a cone, or is it an ice cream, or is it whatever? That goes into Q. The shape of the whole thing, that goes into H. So that's the basic idea here. So now we have all the pieces. So we had two things. We had curry and uncurry, and I said in the previous lecture that I'll leave it as an exercise, but let's implement curry and uncurry. So suppose that we have a function. I will call this one f, and f takes a x and a y and computes x plus y. So this is a function of one variable, and now I would like, and this is in the uncurried form, since it takes a pair, and I would like to convert this f into its curried form so that I can partially apply it. And how could I do that? Well, we can define a function. Let curry, and it takes two arguments. So I'm going to call the first argument the curry, I'm going to call f. And I know that f is going to be a function from a pair, a, b, to c. And then I'm going to have some value x and some value y. So let's see how this works. So curry will take a function which takes a pair and produces a value, and it will take two values and it will produce hopefully the same result as this one. That's the idea of what we want to do. So how would this look like? Well, it would look like this: f, x, comma, y, and that's it. We're done. That is shockingly simple. How does this work? Remember, if we look at this thing and we just partially apply this, right? So this whole thing here has we can say curry has a signature of a pair a comma b to c, and it has an a and it has a b, and it produces a c. So now I call curry with the first argument, which is f, which is this guy up here, which matches you see, f takes a pair. This is a function from a pair to a value. So now I'm just going to call curry with this function here. So now I can say, okay, so now I've used up that argument. Now I'm left with a function that came out of this, which I'm going to call f prime here, which is curry f, and f prime here is going to be a function from a to b to c, which is exactly what we were after, right? And the implementation is simply just, all I have to do when I supply a and b, I just feed them in, create a pair of them, and give them to f, because f accepts a pair. I create the pair, I call f, and I get the c out. Mind bending, but pretty cool. All right, so let's see if we can do the uncurry instead. So uncurry takes a function. So now I'm going to do my f again, and f is going to be of the form a to b to c. So my implementation of f would be f let fxy equals x plus y. And I want to convert this into a function which takes a pair. So I'm going to define my function let uncurry, and that needs to take a function as its first argument. That's the function I want to convert, f, and f has a signature, we already stated up there, a to b to c. So that's just our f. And I want the total result, but I want to apply this on in the end. I want it to take a pair, so that would be a pair P A B to produce a C. So this is how this is. I should say left here. This is type signature of uncurry. So let's implement uncurry then. Let uncurry takes f and it takes x comma y, and the implementation is f x y. I just call f. I unpack the pair and I call f. This here will produce my final result C. And now if I would call just, so I could say let f prime equals uncurry f. So now I just call it, I just skip giving the pair. I just partially apply this uncurry function. So it takes f, and this is a function of two variables, not a single pair, but this is the function of two variables. I pass it into this guy. We can say, okay, what happens? Well, it's going to store it here and wait for me to give a pair. And once I give the pair, I'll unpack the pair and give those. So the type signature of this f prime would be simply the, here's the pair I didn't apply yet. That would be the x, pair of xy to C. So this is, you use a star to mark a pair, but this would be like the tuple. Yes? And that's it. So now we've implemented curry and uncurry. We see how we can transform these functions back and forth. And now we can call them over and over and over again. And if your code is still too fast after doing this, you can just call them a couple more times and you can get it to go really, really slowly. Unless you have a good optimizer. Getting rid of all null ops. Because these are isomorphism. We're going just transforming a function from one form to another. We're not really doing any real work here. We are just playing with functions. So that's the story for today. And in the next lecture we'll talk about lambda functions, which are just normal functions with special names, or lacking special names, I should say. Right.